Folks, so this is a supplemental video lecture I'm recording for you for your first spectroscopy tutorial, Spec 1. So in this tutorial, what you're going to be working on is deconvolution, spectroscopic deconvolution. So here I have a couple examples on the screen. In panel A, this is a XPS X-ray photoelectron spectra. And in panel B, this is an FTIR spectra. And so what you can see in both of these spectra, the thick red line is the actual measured spectra. And the process of deconvolution involves finding a nice functional form of the baseline, which in this XPS data you can see is this dotted line, as well as the peak itself right here. Or similarly, if you have a spectra where there are two competing transitions occurring over a narrow range, such as the example with the asymmetric water stretch and the symmetric water stretch, both occur over a fairly narrow range. And what you get for the whole OH stretching region, for example, is this rather broad peak, which is actually a result of two peaks that lie underneath. And so deconvolution is the process of kind of teasing out those details. So in some spectra, they are found to fit a Gaussian quite well. And you can see here on your document, here is the equation for a Gaussian. In other spectra, such as XPS, it's found that they fit a Lorentzian distribution. And even if you go and read the literature, some folks will even say that sometimes there's a mixed case, a mixed Gaussian, Lorentzian. I'm not going to worry too much about those details. So for now, just for these examples, we'll use a Lorentzian function to fit XPS data, and we'll use various Gaussian functions to fit FTIR data. So I'm going to walk you through how we deconvolute these first two examples and how we do that on Igor, and then you're going to be left to doing a few more examples on your own. So on the Canvas page, you'll find that there's data here in this Excel spreadsheet. So go ahead and open that data. You'll find panel 1A is intensity versus binding energy. That's Y versus X on the XPS. And on the second tab over, there's FTIR data, wave number versus absorbance. And again, that's now this is X for the wave number versus Y for absorbance. Okay, so I'm going to go ahead and open up Igor Pro, and I'm just going to copy paste this data in here, and I'm going to walk you through how I do this example. So first, I'm going to arrange my Igor menus the way that I like to have them. And yes, this is pretty good. And then now I'm just simply going to select this data. I'm going to do a Control-C. I'm going to go to Igor and say Windows, New Table, and just say do it for a blank table. And then say Control-V. And then there's my data. It just goes straight into Igor. So for now, I'm going to go ahead and just get rid of this Excel file. And let's see. So the first thing I can do is say make a new graph just to make sure it plotted right. And we'll have absorbance on the Y and wave number on the X. And I'm going to say do it. And then now just kind of quickly to give a nice working range, I'm going to make the maximum 2800 and the minimum 3800, 3A00. And that's my nice working range of this spectra. And in fact, if you recall, in IR, right, it's backwards. So I'm going to view it from instead 3800 at the minimum to 2800. And then on my left axis, I'm just going to give it some even numbers, make it 0.02 in the top, and I'm going to make it a negative 0.05, just to have an even set of numbers here. And very quickly, I'm not going to worry about formatting this too nicely for now, but just so I know what everything is, I'm gonna label my axes just so I know what they are. Okay. So here we go. So you can see I've got that stretching region loaded up right there. And what I want to do is follow through here on my equations to fit. And my total fit is going to be a result of some function, be it Gaussian or Lorentzian. And note, if we have multiple peaks, it's the sum of all of those Gaussians. So in this water stretching example, we're going to have 2 Gaussians. Plus there's a baseline to consider. And so for now on this example, I'm going to just assume that my baseline is fairly constant. And if I look at this spectrum here, and actually I can go ahead and put on the grid lines. So I'm going to say major only and color those black there. And then I'll do it for the bottom as well. You can actually see here this line at 0, 0. It's actually already coming in as a pretty good baseline. So I probably don't need too complicated of an equation to describe the baseline. Okay. So now what I want to do is say analysis, a curve fitting, just like you did before. And this time what we're going to do under this function, we're going to say new fit function. Okay. And then now I get this menu, and I want to be able to see this Gaussian function right here, because this is the equation that I'm going to enter. And so I'm going to call this total fit. Oops, it doesn't like that. I'm going to say total underscore fit. And I'm just going to make my independent variable x. And so now you can see my function needs to be f of x. And for my fit coefficients, you notice on my table here, I'm going to need A, and I'm going to need peak center position, which I'm just going to call, we'll say x1 for now, and I'm actually going to call this A1 because I have multiple peaks to consider. So we'll say A1, x1. Now I need a parameter for the full width at half max, and I'm going to call that S1. And then, of course, my independent variable I've already said is x. And so now that will give me enough to type in this Gaussian distribution, which I can go ahead and if I note on my notation here, that's going to be A1 times, and I'm going to say exp parentheses. And then that's going to be negative, and then another parentheses, and now that's going to be x minus x1. So again, I'm following this equation right here, okay? And that's all squared. And I'm going to just be really redundant with my parentheses here to make sure it's done correctly. And so then now that's divided by, and then I'm going to say 2 times S1 all squared. And we'll close that off. And then what's nice about this is that you can say test compile, and here it says function compiled successfully. So now that's only one single Gaussian distribution. Okay, so what I really need is, as this document shows me, the sum of all of those. So I'm really going to have a second Gaussian that I want to add on to here. So I'm going to add more fit coefficients, A2, and you can just say down to add another one. And if I follow my same format, I have A1, X1, S1. Now I'm going to have A2, X2, and S2. And then I'm just going to copy paste this. I'm going to say plus this. And now I'm going to make all of my 1s into 2s. Okay, and then I'm going to say test compile. And everything was good to go there. And then now the last thing that I need is some type of baseline function. That's what this b of x function is. Okay? And so I'm going to call, and I just need one single baseline function for this whole thing. And for now, I'm just going to call it a constant. I'm going to call it, well, we'll just call it b for baseline. I'll call it b0. And then I'd have to say, and then plus b0. So I'm just assuming that baseline is a constant. Okay? So I can say test compile function compiled successfully. And I'm going to say save fit function. And then now what I have here is total fit. And if I go down to my list of functions, I can say total fit, and it shows me all of those equations that I need. And this EXP is showing up in a different color, so I think that it's okay, but we'll find out if it's not happy soon enough. And then it also says you have selected a user-defined fit function, so you must enter an initial guess for every fit coefficient. Okay, so I'm going to go through a couple things here. First, I'm going to say on the range, I really only want to fit this from 3,800 to 2,800, right? Because that's what I set up on my range here, all right? And then now when I go over to coefficients, I'm gonna have to start supplying some initial guesses, all right? So remember, A is the peak height. This, what I'm calling now x1, that's the peak center position, and the sigma is the full width at half max. So that literally means what is the width of the peak at half of its maximum value. So I'm just gonna kind of make some of my best guesses. So you can see I've got a max here of like 0.17, but that's the whole thing. So I'm going to guess that maybe that peak number 1 is like 0.1, let's say. And then I'm going to guess that maybe it's somewhere around 3,500 wave number. And I'm going to guess that the full width at half max is maybe 100 wave number. I'm just supplying guesses here. And then now I'm going to say A2 is maybe 0.1. I'm going to say X2 is maybe, you know, I can see a little shoulder here, so maybe like 3,200. And I'm also going to say S2 is like 100, something like that. And then my constant baseline value right here, I'm just going to say 0 because that looks pretty good. And now if I were to say graph now, it automatically puts those guesses on there, which you can see are not very good guesses, but it's pretty close actually. It's not too terrible. And so now when I go and say do it, it's going to converge and try and find the best possible guess. And you can see it didn't do a great job here. So I've got to figure out what went wrong. So I'm going to say go back to analyze and curve fit. This time I'm actually going to clear the range because maybe that didn't make it so happy. I'm going to say graph now again and just kind of see what's going on with my guesses. And I'm going to say do it. And okay, so once again, it ain't happy with something. So let's go and make sure that, oh, you know what the last, you know, we didn't do? Aha. My Y data needs to be absorbance. My X data needs to be wave number. That's what I didn't do correctly. So now I should just be able to say do it. And there we go, beautiful. Okay, it comes up with this nice fit. And if I go to my command history here, you can see I've got all of those values listed. They're kind of small, but all the same, there they are. And if we want to make sure that we had the error analysis going on here, under my output options, I'm going to go ahead and select error analysis. We'll make it at the 95th confidence interval. And when I go ahead and say do it, I should have updated confidence intervals based on the 95th percent. And there they are. And you can see they can be quite large, right? This is saying 3416 plus or minus 56.7. And you know, this is saying 3257 plus or minus 84. And that's okay. That's what we're going to get. But you also notice here that my baseline isn't great. For my constant baseline value, it said a value of 0.01. And so that's what it's reading off. You know, if I were to add some extra ticks in there, yeah, there it is. So, you know, there's 0.01, 0.02, and this is reading 0.016. So that baseline, you know, maybe needs to actually be some kind of an equation of sorts. So I'm going to go back here, and I'm going to go back to curve fitting. And on my total fit, I'm going to say edit fit function. And then now, just as a guess, I'm going to say B0 times X. So that's, instead of assuming that it's a constant, it's going to assume that perhaps it's a line. I'm going to say test compile, function compiled successfully, and I'm going to say replace fit function. And then now, because I still have some of these initial guesses, that should be okay. I just pushed graph now, and I'll push do it again, and let's see. So still not coming in so great on that baseline. So maybe I'm just going to make a guess here, and instead of it being some type of line, I'm going to say the b0 times maybe x squared. At this point, I'm just kind of doing my best guess. That's what data fitting is all about. So I updated that to baseline times x squared, and I'm going to say do it. And look at that. It's getting a little bit better. And if I go down the line even more, let's make it x cubed. Why not? Replace fit function, do it, and hey, look at that. That's pretty good. And what I'm really looking for is just kind of a qualitative, does it hit all of those data points? So I think that looks pretty good to me. And here you can see that I've got all my new fit parameters. You kind of have to accept them, with these large plus or minuses. That's going to happen. But, when we look at how all these values were changing, my very first guess, it was coming out as 3277 and 3430. And then my next guess was 3437 and 3290. And then the final thing is 3429 and 3230. So those aren't really changing a whole lot. Of course, there is some fairly large error in those parameters, but that's okay. So now I'm just going to make this a different color so that it stands out. And what we've done here is it gives me like a total fit. So if you want to see, all of these individual contributions here, then what we have to do is actually make new equations out of those individual fits. So I'm going to include that code on the tutorial file. But as a reminder, I can use the make function. So I'm going to go ahead and type that live so you can see what I'm doing. And I'm going to say make /n equals 1,000. So I'm making new waves with 1,000 data points. And I'm going to say space, and I'll call that baseline, and then peak 1, and then peak 2, because really I have 3 equations I want to show you. I'm going to show you what the baseline equation is, what the peak 1 is, and what the peak 2 is. And I'm going to say enter, and then I'm going to say set scale. And I'm going to say x, 2800 to 3800, because that's what we fit our data over. And we'll say that that's baseline, peak 1, and peak 2. Wasn't happy about something there. So let's see, what did I do? Maybe a space. Or I think maybe it wants a comma. Okay, beautiful, it was a comma. Okay, so what we've done is now we've made n equals 1,000 data points spread out over 28 to 3,800. So we're going to have a nice smooth line. And the first function I'm going to define is baseline. And I'm going to say baseline equals. And so remember, we just said it's this b constant times x cubed. So I'm just going to grab this number here, that negative 5.0735 times 10 to the negative 14. And I'm going to say it's this number times x. And then now that function is defined. And over here, I'm going to right click and say append traces to graph. And now I want to say baseline on the y versus calculated on the x this time. And we'll go ahead and say do it. And there it is. There's that individual equation. And let's go ahead and give it something so that it looks different. Okay, great. And I'm going to move this picture out of the way so we don't get confused what we're looking at. Okay, so there's my baseline equation. Now I want to graph peak number 1. So I'm going to say peak 1 equals. And then now I'm going to follow the form of my Gaussian equation right here, but I'm going to fill in all of my parameters. So I'm going to say that 0.096966 times exponential. And actually here it tells me that I can use a lowercase e, and that works too. Exponential, and then I'm going to be really redundant with my parentheses. So I'm going to say that's x minus, and then of course it's 3429.5, and then that's all squared. And then now divided by 2 times the full width at half max. And for this one, that was 112.68. And let's see, that's the full width at half max is squared. And I'll put a parenthesis around that. And then I think I'm ready to close my exponential. And we'll say enter. And then now let's make sure we got it correctly. So I'm going to right click in my graph, say append to traces. And I'll say peak 1 on the y and calculate it on the x. And let's say do it. And cool, there it is. And once again, I'll just give that a different color so I know that it stands out. Great, so there's peak 1. And then now peak 2, I can define the exact same way, but I'm going to use the peak 2 coefficients. So it's 0.089581 times exp parentheses, and then again, be really redundant with your parentheses, 3298.6, and that's all squared. And then now divided by 2 times the full width at half max squared. So 135.79 squared. All right, and then now close the exponential. Okay, so now I've entered that in, and now I should be able to right click over here, say append traces to graph, and now peak 2 versus calculated, and then do it, and voila, beautiful. So there's the second peak, which of course belongs to the symmetric stretch. The first one we did belongs to the asymmetric stretch. And then now we've deconvoluted the 2 peaks. We've deconvoluted the background. And of course, our total fit, as you can see from this equation right here, right, is the background plus the sum of all of those other peaks. And so to finish making this a nice and polished document, you can go ahead and load it up in the layout mode and use all of those drawing features to highlight all the pertinent information that you want to highlight. Okay, so from here you should be able to do the next XPS example, and you'll find a few more examples that you'll be tasked with doing on your own. Okay, happy deconvoluting.